Now let's start talking about memory units and how different memory structures can represent different types of data. In computers, information is always stored and represented by bits. Bits are binary digits, which serve as the smallest memory units and represent all sorts of data in computers, including numbers, letters, sounds, and colors. Each bit can hold one out of two values, either 0 or 1. Zeros and ones can be represented in computers using electrical voltage or current pulses, whereas the state of voltage equals 1 and the state of no voltage equals 0. Processors are capable of interpreting and running sets of commands that were composed by zeros and ones. Those sets of commands are part of what we call machine code or binary language, where each bit is represented by a single digit, either 0 or 1. Numbers in binary are traditionally read from right to left. Different combinations of bits will represent different values in applications. Depending on the standard protocol and the application which are used to read the bits, the interpretation of their pattern may differ. For instance, the binary combination of 100001 when converted to decimal value will give us the number 65. Now, if the application is converting the signal to letters using the ASCII standard, it will give us the letter A. Many free calculators and tools are available online for the conversion of values from one standard to another, such as hexadecimal counting, decimal counting, binary counting, letters, colors, other counting methods, and so on. In this example, I have used a longer binary combination. This combination equals to 44,288 in decimal counting and to this specific shade of green in 16-bit color architecture. 16-bit gives us 65,536 possibilities. So a 16-bit color architecture stands for an architecture that contains 65,536 different color possibilities. Therefore, when a decimal value has 16 characters, it is most likely intended to be interpreted by a 16-bit application or higher. Now that we have covered and understood the smallest and most fundamental memory units, we can review larger memory units, which are composed by the same bits. In order to fully understand the scale of each unit, we would have to compare each one of them to different types of data we use in our daily lives. So let's start with a bit. A bit represents one out of two possibilities, either 0 or 1. One bit can store the logical value of voltage. 0 equals no voltage and 1 equals voltage. The next unit is called a byte. One byte simply equals 8 bits. One byte can store a single character, for example, a letter or a number. If you open Notepad and type in only a single character and then save the file on your desktop, you can right-click the file and then go to Properties. In the Properties, you will notice that that single character takes only 1 byte or 8 bits. The next unit is called a kilobyte. 1 kilobyte equals 1024 bytes or 8192 bits. 1 kilobyte can store a short text file up to 1000 characters long. Next is a megabyte, which equals approximately 1 million bytes or 1000 kilobytes. 1 megabyte can store 2 to 3 low-quality photos or a short MP3 soundtrack. A gigabyte is composed of approximately 1000 megabytes or 1 million kilobytes. 1 gigabyte can store a full-length high-definition movie or 250 MP3 songs. Next unit is called a terabyte. A terabyte is composed of approximately 1000 gigabytes or 1 million megabytes, and it can store more than 500,000 Kindle ebooks. Next we have a petabyte, which is approximately 1000 terabytes or 1 million gigabytes. 1 petabyte can store 700,000 full-length high-definition movies. Next we have an exabyte, and just like the previous, an exabyte equals approximately 1000 petabytes or 1 million terabytes. Just so you get a brief idea of how big an exabyte is, several hundreds of exabytes of data are transferred over the internet each year. Next we have a zettabyte. A zettabyte equals approximately 1000 exabytes or 1 million petabytes. As for 2019, all the data in the world is estimated to be only a few zettabytes. And lastly, we have the yottabyte. The yottabyte equals approximately 1000 zettabytes or 1 million exabytes. This term only exists in theory but doesn't really have a practical use nowadays.